Yo, what's up, everybody? So today we're talking about proving trig identities. I know you can't read it, so that's the problem, and I don't care. So, proving trig identities. So, in the last video, we talked about identities and so many identities, and hopefully you know most of them or have some idea or some layout of them. So, we're going to be using them today to prove useless identities. So now we know the useful ones, and now we're going to use them to prove the useless ones, and it's going to be great. The main part of these exercises that I'm going to be giving you is not so you can know the theorems, but so that you can know how to prove any theorem, any identity, that is. And it's a good skill to have in your tool belt. It's a good tool to have in your tool belt. There we go. It's a good skill to have in your skill belt. That'll be great. Okay, so an example is prove the following trigonometric identity. Sine of x over 1 minus cosine of x equals 1 plus oopsie daisies 1 plus cosine of x over sine of x. You can do this many ways. What I'm going to do is I'm going to do cross multiplication. So usually when you see these, you want to try to find a way that you can multiply or add or combine some of the functions, so you can manipulate them to form using our old identities that we learned to manipulate them and do stuff like that. So if you do, so I haven't done this problem, or if I did, I forgot it. But if you cross multiply, you get, or simply multiply by 1 minus cosine of x and then multiply by sine of x, then you get sine of x squared, so sine squared of x equals 1 minus cosine squared of x. Add cosine squared of x to both sides, you get sine squared of x plus cosine squared of x equals 1. And we know this. So our goal is to really just make some completely useless identity into and manipulate it so that we're really just getting an identity that we know and that we at least should know, and that's useful. Okay. Congrats, you solved a problem, hopefully. By the way, I want you to try these. So pause the video when I give you a problem and please try it. Now, this one's a little harder. Prove that the cosecant of theta, times the cotangent of theta. Oh god, that went really sloppy. Times the secant of theta equals secant squared of pi over 2 minus theta. So usually when you have these cosecants, cotangents, secants, I usually like to convert them into sines and cosines. Because remember how I said you need to know sines and cosines, and then like I wasn't gonna do the sum angle formula for tangent, because that's equal to the sine for the sum angle formula for sine over the sum angle formula for cosine. So we can use that here, kind of. We can manipulate, so we can say the cosecant of theta is 1 over sine of theta, and that times cotangent of theta is sine theta over cosine theta. That times secant theta is 1 over cosine theta, and that's equal to secant is 1 over cosine, so we have 1 over cosine squared of pi over 2 minus theta. Nice. So now, so now what I do is I say, that's so cool, let's cross those down. And now we have 1 over cosine squared of theta equals 1 over cosine squared of pi over 2 minus theta. Obviously you see some symmetry, and we can do some algebraic manipulation to get to something else. So we can take the reciprocal and then square root both sides, and we get cosine of theta equals cosine of pi over 2 minus theta. Now, what's wrong with the step I'm going to do? Do inverse cosine on both sides, and you get theta equals pi over 2 minus theta. What's wrong with that? Well, you can't do that because, remember, when we have our graphs, the cosine is a periodic function. So it goes like that, and it goes on to forever on both sides. So an inverse is flipped over the line y equals x. So if you were to flip this, you would get kind of like a sideways kind of one, right? And that is not a function because there are many x values that have the same, there are many y values that have the same x value. And remember the vertical line test, where you can put a line right through it, and you can put a line right through any of the points, a vertical line, and if that vertical line crosses 2 or more points on that graph, it's not a function. Hopefully I went over that. If I didn't at this point, I'll make it later. But yeah, you can see that there are many points with the same x value but different y's. So that's not a function. So we can't do inverse cosine because there's many values. So what we do, like doo-doo. So what you do is you can still look at the graph. And wait, I want to draw this accurately, a little more accurate. Oops. God, I'm not good at this. Oh my god. Okay, notice it crosses at 0, 1. That's what I wanted to do, or illustrate. So, we notice that the period of this function is pi, right? What am I doing? Yeah, so now we can, so notice that this is just equal to the cosine of theta minus pi over 2. If you're wondering why that is, that's because we know that the cosine of x equals a negative, or equals cosine of negative x, right? Right? So now we can do that here, and we can take the negative of pi over 2 minus theta, and we get theta minus pi over 2. So, let's say we had the cosine of theta, so that'd be like somewhere here. Yeah, sorry. So now, if we do minus pi over 2 on this, or if we did theta minus pi over 2, wait, so yeah, this is theta, right? This is theta, and if we did theta minus pi over 2, we'd end up here maybe. And then it'd be at the same point. I think I messed this up, but whatever. We're just gonna look back and maybe we can do a different thing. So, yeah. Oh, I think I know what I'm supposed to do. I'm just a dumb bum. Oh, I'm such a dumb bum. This is just, we notice that this side is just cosecant square root of theta, and this side becomes cosecant square root of theta, and this side is 1 over cosine square root of theta, which is also cosecant square root of theta. And guess what? They're equal. Yay. Wait, what am I doing? Huh? Oh, cotangent is cosine over sine. Tricked myself. So these cancel, and then you have 1 over sine squared of theta. And that's obviously equal to cosine squared of theta by definition. Kind of. Right. Sorry about that inconvenience, guys. I don't really trig. I don't trig very well, so yeah. Oh well. Next thingy-majig is let's prove that this is going to be the last one for this video. I just want you to get the idea of how to do these, and then you can go on your own. Sorry. So secant to the fourth of theta, and I know you see the fourth like, oh my god, what is that thing doing there? But just trust me, it gets nicer. Minus tangent to the fourth of theta, and you're like, okay, I know what to do. Difference of squares, obviously. So now here you have 1 plus sine squared of theta over cosine squared of theta. So prove this. I'll give you a moment. Okay, let's do this. So we realize right away that this is just secant of theta times tangent of theta. What am I doing? Oopsies. Oh wait, no, sorry. Secant of theta minus tangent of theta times secant of theta plus tangent of theta. Notice that this just becomes secant squared of theta minus tangent squared of theta. And then we have our secant squared of theta plus tangent squared of theta. Right? I just factored out the secant squared of theta minus tangent squared of theta ahead of time. And now that is equal to, you know what? I'm just not gonna do this. I think that'll be better. So secant squared of theta minus tangent squared of theta. Okay, there we go. That is equal to, let's still, hey, guess what, bro? That's still equal to 1 plus sine squared of theta over cosine squared of theta. So usually now you want to try to manipulate these into something that you can use. So in the last one I couldn't really do anything, but in this one, you might notice that this is just 1. Why is that the case? Or wait, is that equal to 1? Yeah, that's equal to 1. Okay. Why is that the case? Well, remember, sine squared of theta plus cosine squared of theta equals 1. If you divide by cosine squared of theta on both sides, you get sine squared of theta over cosine squared of theta, which is tangent squared of theta, plus cosine squared of theta over cosine squared of theta is 1, equals 1 over cosine squared of theta, which is secant squared of theta. Now, notice that if you subtract tangent squared of theta on both sides, this is just 1, so we can use that. If not, you do at least notice the secant and theta, and you do remember the thing. So yeah, yeah. And if you don't still, then that's equal to 1 over cosine squared of theta minus 1 or minus sine squared of theta over cosine squared of theta. They already have a common denominator, so you get this, and this is cosine squared of theta. At least you know that. And this becomes 1. There, simple. Now let's do some things, and yeah. So now we just have to prove that secant squared of theta plus tangent squared of theta equals 1 plus sine squared of theta over cosine squared of theta. What's good about proving identities is that you know that they're true. So if you know that they're true, you can use that. Remember in the proofs video when we talked about induction? The thing with induction was that we had to know that it was true. We had to know where we were going to go. And if we do that, then we were using the fact that we knew it to prove the statement. So in this case, we can't really use induction, but we know that it's true, and we're just manipulating both sides to get something obvious, like sine squared of theta plus cosine squared of theta equals 1, right? In this case, we have to do something else. So now, what I like about this side is that we can break this up. So we can say that's equal to 1 over cosine squared of theta plus sine squared of theta over cosine squared of theta. Maybe we did that a little earlier, but I do it now because we simplified this left side completely. notice this is just secant squared of theta. This is tangent squared of theta. And we have the obvious thing. Secant squared of theta plus tan squared of theta equals secant squared of theta plus tan squared of theta. Subtract them on both sides. Guess what? 0 equals 0. Yay. Now we can stop here or we can stop here. Either way. Yay. And we did it. So, yeah, hopefully this wasn't too much of a hassle, but I just had to make this video because it's trig, and it's not just about knowing that knowing those are true. And I don't think this is really an important thing to memorize, but maybe if you have some assumption, you can prove it. And maybe like just knowing how to do that improves your problem solving abilities a lot. So yeah, thanks for watching. I'll see you guys next time. Goodbye.